Tonight, we're going to talk about the most violent thing that happens in the universe. Not a collision between galaxies, not the Big Bang itself, but the birth of a black hole. And when I say violent, I don't mean violent the way a storm is violent, or the way an explosion is violent. I mean something else entirely. I mean a star larger than anything our brains can genuinely picture. A star that might span hundreds of millions of miles. A star that has been burning for millions of years, collapsing down to something smaller than a city in less than a second. Not slowly, not gradually, in less than a second. That's what we're talking about tonight. If you find comfort in these gentle explorations of space and science, I'd be grateful if you'd consider subscribing and giving this video a like. I'd love to know where you're watching from and what time it is for you. Feel free to drop your location and time in the comments below. Most people have heard of black holes. They show up in movies, in textbooks, in every conversation about space that goes longer than 5 minutes. But here's what most people don't realize. Almost nobody understands how they're actually born. Not the mechanics, not the sequence, not the specific, terrifying chain of events that takes a living star and converts it into one of the most extreme objects the universe is capable of producing. The birth of a black hole isn't just dramatic in the way that space things are generally dramatic. It involves physics operating at the absolute edge of what matter is allowed to do. Here's the scale of what we're dealing with. The star that becomes a black hole might be 20, 30, 50 times the mass of our sun. The sun, remember, could hold about 1.3 million Earths inside its volume. A star 50 times more massive than that is something our intuitions simply aren't built to process. It is enormous in a way that numbers can describe, but our minds can't really hold. And that entire object, all that mass, all that volume, all that energy, collapses inward under its own gravity and forms a black hole with an event horizon just a few miles across. You could drive across it, all of that, compressed into something you could drive across. We're going to walk through the entire process tonight. We'll start with what a star actually is, why it exists in the first place, what keeps it stable for millions or billions of years. Then we'll trace the fuel chain, the sequential stages of nuclear burning that a massive star goes through as it runs out of options. Each stage faster than the last until it hits a wall it cannot cross. We'll look at the collapse itself. That happens on a timescale so short that the word sudden barely covers it. And we'll end at the moment a black hole actually winks into existence, the moment an event horizon forms. The moment a region of space-time becomes permanently sealed off from the rest of the universe. We've also, for the first time in the history of astronomy, actually watched this happen. Not theorized about it, not reconstructed it from indirect evidence decades after the fact. Watched it. Recent observations have given astronomers a real-time window into stellar collapse events. What we've seen has confirmed some of what the physics predicted and complicated the rest. That's worth understanding too. Black holes have a reputation for being abstract, distant, theoretical. Something that exists out there, somewhere, in the far reaches of space, unconnected to anything that matters here. But the process that creates them is written into the physics of every atom of heavy matter in the universe. The iron in your blood was forged in a stellar core. The oxygen you're breathing was produced in the same kinds of fusion processes we're going to describe. These events are not distant abstractions. They are the mechanism by which the universe builds and rebuilds itself. They happen at a scale of violence that nothing else in nature comes close to matching. So that's where we're going tonight. From a living star to the moment it ends, step by step, through the actual mechanics of what happens and why. No shortcuts, no hand-waving, just the physics, in the order it actually occurs, at the scale it actually operates, and the process that creates it is so extreme, so catastrophically fast, that understanding it changes how you think about matter, about gravity, about what the universe is actually capable of doing. Let's start with something familiar, our sun. Every morning it rises. It lights the sky. It warms the ground. From down here on the surface, it looks small enough to cover with your thumb. Harmless, easy to ignore. But the sun is not small. The sun has a diameter of about 864,000 miles. You could line up 109 Earths side by side across its face. Its volume is large enough to hold about 1.3 million Earths inside it. Every mountain, every ocean, every city, every living thing on this planet exists on a world whose entire volume is less than 1/1,000,000th of the sun's interior. The sun contains 99.86% of all the mass in our solar system. Everything else combined, every planet, every moon, every asteroid, every speck of dust floating between the worlds, makes up the remaining 0.14%. That's how completely the sun dominates everything around it. And yet, in cosmic terms, the sun is ordinary. Astronomers classify it as a G-type main sequence star, a yellow dwarf. There are billions of stars just like it scattered through the Milky Way alone. The sun is not special. It's not large. It's not particularly bright. It's an average star living an average life in an average galaxy. And understanding what it actually is tells us something important about what a star actually does. A star is not just a ball of hot gas sitting in space. It's a war. Two forces locked in a constant struggle, and the star only exists because neither side is winning. Gravity wants to crush the star inward. It has always wanted to do this. From the moment a cloud of gas and dust began collapsing under its own weight to form the sun, gravity has been pulling every atom toward the center. Left unchecked, it would compress the sun down to nothing. But gravity doesn't win, and the reason it doesn't win is fusion. Deep inside the sun's core, the pressure and temperature are so extreme that hydrogen nuclei are forced close enough together to fuse. 4 hydrogen nuclei combine to form one helium nucleus, and in that process, a tiny fraction of mass is converted directly into energy. This is what Einstein's equation actually means in practice. Mass becomes energy. That energy radiates outward through the sun's interior, creating pressure that pushes back against gravity. The star finds an equilibrium. It settles into a stable size. It holds that size for as long as it has hydrogen to burn. The sun has been burning hydrogen for about 4.6 billion years. It has enough left to keep burning for another 5 billion. That's a long life, a stable life. The sun burns through roughly 600 million tons of hydrogen every single second, and it has so much hydrogen that this rate of consumption barely makes a dent over millions of years. It is, in the most literal sense, an enormously slow fire with an enormous fuel supply. Now scale up. Imagine a star not 1 times the mass of our sun, but 20 times the mass. Here's what most people don't realize about massive stars. More mass does not mean a longer life. It means a shorter one, a much shorter one. The reason is gravity. A star 20 times more massive than our sun has enormously more gravity pressing down on its core. To push back against that gravity, the core has to generate far more pressure. More pressure means higher temperatures. Higher temperatures mean faster fusion rates. The star burns through its fuel not 20 times faster than our sun, but hundreds of times faster, thousands of times faster. A star with 20 times the sun's mass might live for only 8 to 10 million years. Our sun will live for 10 billion. That 20 solar mass star burns brilliantly and briefly, like a fire that roars hottest just before it goes out. Push the mass higher. A star 50 times the mass of our sun burns so intensely that it might exhaust its core hydrogen in just a few million years. These stars are rare. They're tremendously luminous. They pour out more light in a single day than our sun produces in thousands of years. You can see them from enormous distances. They are genuinely spectacular objects, and they are running out of time almost from the moment they form. This is the pattern. Low-mass stars like red dwarfs burn so slowly and so steadily that they can survive for trillions of years, far longer than the current age of the universe. Medium-mass stars like our Sun burn for billions of years and end their lives relatively gently, swelling into red giants before shedding their outer layers. But massive stars, the ones 10, 20, 50 times the mass of our Sun, burn fast, burn bright, and face a very different kind of ending. The relationship between mass and lifespan is not gentle. It's steep. It's almost brutal. Double a star's mass and you don't have its lifetime. You cut it down far more dramatically than that. The most massive stars known to exist live for only a few million years. In cosmic terms, that's barely any time at all. The Earth has orbited the Sun about 4.6 billion times. One of these massive stars might complete only a few million orbits around its galaxy before it's done. It forms, it blazes, and it dies before most stars have even settled into the early stages of their lives. Why does mass matter this much? Because fusion rate scales with temperature, and temperature is driven by the weight pressing down on the core. More mass means more gravitational pressure. More pressure means hotter core temperatures. Hotter core temperatures mean faster reactions. Faster reactions burn through the available fuel faster. The star is essentially a pressure cooker, and the more you load onto it, the hotter it gets, and the faster it consumes what's inside. This is what makes massive stars so significant when we talk about black holes. The same property that makes them spectacular, their enormous mass, is the property that guarantees their eventual collapse. They can't help burning fast. They can't slow down. The physics of their interiors forces them to consume their fuel at a rate that makes their deaths not just possible, but inevitable, and soon. A star 20 times the mass of our Sun is not going to live long enough to see the universe grow much older than it already is. It will exhaust what it has, and then the war between gravity and fusion will end, and gravity will finally get what it has always wanted. The more mass a star is born with, the brighter it burns, the faster it exhausts its fuel, and the more violently it ends. And for the most massive stars, that ending is something else entirely. When a star exhausts the hydrogen in its core, it doesn't simply stop. The star has spent millions of years fusing hydrogen into helium, building up an ash pile of helium at the center. That helium just sits there. It's inert at the temperatures the core can initially reach. But the star hasn't given up. Gravity is still pressing in from every direction. The core, without fusion to hold it up, begins to contract. As it contracts, it heats, and eventually it gets hot enough to do something remarkable. It starts burning the ash. The helium that was left over from hydrogen fusion becomes the next fuel source, and the star buys itself more time. This is the pattern that will repeat over and over again, each cycle shorter than the last, each one more desperate than the one before. Hydrogen fusion runs at core temperatures of roughly 10 million degrees. At those temperatures, the reaction rate is slow and steady. A massive star, one with 20 or 25 times the mass of our Sun, might spend 8 or 9 million years in this phase. The core is converting 4 hydrogen nuclei into 1 helium nucleus, releasing enormous amounts of energy each time. It's a productive reaction. Each fusion event gives the star good value in return. The energy yield is high. The timescale is long. Across millions of years, the star glows steadily, burning through its hydrogen supply at a rate that feels, cosmically speaking, almost patient. Then the hydrogen runs out. The helium core contracts, heats up, and ignites. Helium fusion requires temperatures around 100 million degrees to get started, about 10 times hotter than hydrogen fusion. At those temperatures, helium nuclei begin fusing into carbon and oxygen. The reaction rate is faster. The energy released per reaction is lower. The star is running a less efficient engine now and running it harder. The helium burning phase for a massive star lasts perhaps a few 100,000 years. That's still a long time by human standards. It's less than a blink by the standards of the hydrogen phase. The star has taken its first step toward a pace it can't sustain. Something important is happening here that's worth pausing on. Each time the star ignites a new fuel source, it has to run its core hotter than before. Hotter cores mean faster reactions. Faster reactions burn through the available fuel more quickly, and less energy comes out per reaction with each successive fuel type. The star is caught in an accelerating cycle that it cannot reverse. It's not burning more fuel to get more energy. It's burning more fuel just to generate enough pressure to keep itself from collapsing. Every stage is a little more frantic than the last. When the helium is gone, carbon is left behind in the core. Carbon fusion requires temperatures above 500 million degrees. At those temperatures, carbon nuclei begin fusing into neon and magnesium. The energy released is lower still. The reaction rate is higher. The carbon-burning phase in a massive star lasts perhaps a few thousand years. The star has gone from millions of years down to thousands. The acceleration is already startling, and we're not close to the end yet. After carbon comes neon. Neon burning is strange compared to the earlier stages. The core temperatures required around 1 billion degrees are so high that photons in the core have enough energy to actually break neon nuclei apart before fusion can happen in the traditional sense. What follows is a rapid series of reactions involving the freed nuclear fragments. The neon burning phase lasts roughly a year. 1 year. The star that spent millions of years on hydrogen has now moved through an entire fuel stage in about the time it takes Earth to complete one orbit around the Sun. Oxygen follows. Oxygen burning requires temperatures somewhere above 1 billion degrees. At those conditions, oxygen nuclei fuse into silicon and sulfur. The oxygen burning phase lasts a few months. The compression of timescales at this point is almost difficult to track. We've gone from millions of years to hundreds of thousands to 1 year to months, and the star is still not done compressing its own timeline. Here's what most people don't realize about this process. The outer layers of the star have no idea any of this is happening. The star's surface is still glowing. It still looks, from the outside, like a massive star doing what massive stars do. But the core has been through an extraordinary sequence of transformations. It now has a layered structure, like an onion. Silicon and sulfur are sitting in the innermost shell, burning. Oxygen is burning in the layer above that. Carbon is burning above the oxygen. Helium above the carbon. Hydrogen, in some cases, still burning in the outermost shell. Each layer is fusing a different fuel. Each layer is producing the ash that feeds the layer below it. The star has become an extraordinarily complex and accelerating machine. And then comes silicon burning. Silicon fusion requires core temperatures above 3 billion degrees. At those extremes, the reactions proceed through a cascade of rapid processes that don't look much like simple fusion anymore. Nuclei are constantly being assembled and disassembled by the ferocious temperatures, and the net result is the production of iron group elements: iron, nickel, cobalt. The silicon burning phase lasts about 1 day. 1 day. The star that spent millions of years burning hydrogen has now arrived at a fuel stage that runs to completion in roughly 24 hours. Think about that contrast for a moment. The hydrogen phase lasted 9 million years. The silicon phase lasts a single day. The entire sequence, hydrogen to helium to carbon, to neon to oxygen to silicon to iron, has compressed from geological timescales down to something measured in hours. Each stage was the star reaching for the next handhold on the cliff face. Each stage gave it a little less time than the last. The debt has been compounding the entire time, and now the bill is almost due. The reason for this acceleration is built into the physics. Higher temperatures drive faster reaction rates. That much is intuitive. But the energy released per reaction also drops at each stage. Hydrogen fusion is among the most energy-efficient nuclear reactions available in nature. Helium fusion releases less. Carbon less still. Each successive stage returns less energy for the fuel consumed, which means the star has to burn faster and faster just to maintain the pressure it needs. It's like running harder and harder just to stay in place, and every lap costs more than the one before. What this means for the core is that by the time silicon is burning, the star is living on borrowed time measured in hours rather than millennia. The silicon burning shell is producing iron at a rate the star cannot use. Iron piles up in the innermost core. It doesn't burn. It doesn't contribute any pressure. It just accumulates. The iron core grows heavier with every passing hour, and the star, having burned through every available fuel source at an increasingly desperate pace, is finally running out of options. And then the core produces iron, and that's where everything stops, because iron is the end of the line. Fusing iron doesn't release energy, it absorbs it. That distinction sounds small, but it's everything. Every previous stage of fusion, hydrogen to helium, helium to carbon, carbon through to silicon, released energy outward. That outward energy created pressure. That pressure held the star up against gravity. Iron ends that arrangement completely. To understand why, you have to look at what's actually happening inside an atomic nucleus. Protons and neutrons are bound together by what physicists call the strong nuclear force. The tighter they're bound, the more energy you'd need to pull them apart, and the less energy you can extract by fusing them further. Physicists measure this as binding energy per nucleon. It's essentially a measure of how stable a nucleus is. And iron sits at the peak. IRON 56 is the most tightly bound nucleus in nature. It's at the top of that curve. Everything lighter than iron releases energy when fused together, because you're moving up the curve toward greater stability. Everything heavier than iron releases energy when split apart, which is why uranium can power a reactor. But iron itself sits right at the summit. There's nowhere higher to go. You can't extract energy by fusing iron into something heavier, because that would take you back down the other side of the curve. The reaction runs in the wrong direction. It costs energy instead of releasing it. For a star, this is catastrophic. The entire machine has been running on the principle that squeezing lighter nuclei together produces energy. That energy heats the core. That heat generates pressure. That pressure resists gravity. Remove the energy output and you've pulled the foundation out from under everything. But the iron doesn't accumulate all at once. That's what makes this stage so insidious. Silicon fusion in the shell surrounding the core keeps producing iron and depositing it downward. The iron core grows steadily. It sits there, inert, unable to generate any outward pressure from fusion, simply accumulating more mass. The core gets heavier, gravity presses down harder, and there's no new energy source coming to the rescue. So what's actually holding the iron core up during this period? The answer is something called electron degeneracy pressure, and understanding it requires stepping briefly into quantum mechanics. Electrons don't behave like ordinary particles at extreme densities. Under normal conditions, electrons in a gas simply bounce around and generate pressure through heat, the same way any gas pushes outward when compressed. But squeeze matter tightly enough, and something different takes over. There's a rule in quantum mechanics called the Pauli exclusion principle. It says that no two electrons can occupy the same quantum state at the same time. They're forbidden from it. And when matter is dense enough, electrons start running out of available states to occupy. They can't simply pile on top of each other. They resist. They push back. This resistance is electron degeneracy pressure. It doesn't depend on temperature the way normal gas pressure does. It's purely a consequence of quantum mechanics, of the fundamental rules that govern how particles can be arranged. You can cool the core down and electron degeneracy pressure doesn't change. It just exists. As long as those electrons are packed closely enough together, for a while, this is enough. The iron core sits there, growing heavier, unable to generate fusion energy, and electron degeneracy pressure holds it in place. The star continues burning silicon in the shell above. More iron rains down. The core grows more massive. Electron degeneracy pressure keeps pushing back, but it has a limit. In 1930, a physicist named Subramanian Chandrasekhar calculated that limit while he was still a teenager on a steamship crossing the Indian Ocean. He worked out that electron degeneracy pressure can only hold up a white dwarf, or in this case an iron core, up to a certain mass. Above that mass, the electrons simply can't generate enough resistance. They get squeezed into the protons. The quantum rule still applies, but gravity has become too strong for the rule to matter anymore. That limit is approximately 1.4 times the mass of our Sun. We call it the Chandrasekhar limit, 1.4 solar masses. That's the threshold. That's the number that separates a stable iron core from catastrophe. Think about what that actually means for the star. It has spent millions of years fusing hydrogen. It has moved through helium, carbon, neon, oxygen, silicon. Each stage has been buying time, maintaining some semblance of equilibrium, keeping the collapse at bay. The star has been living on borrowed energy, converting mass into light and heat, stage by stage, moving through the elements. And now the iron core is sitting there, growing heavier by the second from the silicon burning above it, closing in on 1.4 solar masses. And the only thing holding it up is a quantum mechanical rule about electrons. When the iron core crosses that threshold, electron degeneracy pressure doesn't gradually weaken. It fails. Almost instantly, the electrons that have been resisting compression get forced into the protons. This process, called electron capture, produces neutrons and releases enormous numbers of particles called neutrinos. The neutrinos stream outward at nearly the speed of light. And suddenly, the core has lost the only source of pressure it had left. Gravity has been pulling inward the entire time. Now there is nothing pushing back. What follows happens faster than any human timescale can comfortably express. The iron core, at this point roughly the size of Earth, with a mass greater than the Sun, begins to collapse. Not gradually, not over millions of years like the hydrogen burning phase, not over centuries, not even over hours or days or seconds in any comfortable sense. The collapse of the iron core takes less than a second. In that fraction of a second, a structure the size of our entire planet is compressed to a sphere roughly 12 miles across. The density achieved during this collapse exceeds anything else that exists in the universe under normal conditions. A teaspoon of this collapsing material would weigh more than 1 billion tons. But before we get to that, before we get to what the collapse actually looks like and what it produces, it's worth sitting with what the iron core represents as it approaches the limit. This is a star that has been alive for millions of years. It has fused its way through most of the periodic table. It has generated enough energy to outshine our entire galaxy for the duration of its life. And now, the thing that ends it all isn't an external collision or some outside force coming in to destroy it. It's a single rule about nuclear binding energy. Iron is stable, that's it. Iron is simply too stable to give anything more. The silicon burning shell keeps running. Iron keeps accumulating. The core keeps growing. Each additional fraction of a solar mass brings it closer to the edge. The electrons push back with everything quantum mechanics will allow them. The iron core keeps growing shell by shell until it crosses the point of no return. And then, in less than a second, the entire history of the star becomes irrelevant. The collapse begins, and it happens in a way that almost nothing in our everyday experience can prepare you for. The iron core at the center of this dying star is roughly the size of Earth. That's where we start. It contains about 1.4 times the mass of our Sun, packed into a sphere perhaps 8,000 miles across. In under a second, that sphere compresses down to roughly 12 miles across. 12 miles. That's the size of a mid-sized city. You could drive across the object this star becomes in about 15 minutes. And somehow, the mass hasn't gone anywhere. It's all still there. Every atom that made up that iron core is still present, just crushed into something our instruments can barely describe. The numbers here don't behave the way numbers normally do. What triggers this is gravity. Pure, unchecked gravity. The moment electron degeneracy pressure fails, and we talked about exactly when that happens, there's nothing left to push back. The force that has been straining against the core's weight for the entire star's life simply loses, and gravity wins instantly. The core doesn't ease into its collapse. It doesn't slowly compress over years or centuries. It falls. The outer layers of the iron core crash inward toward the center at roughly a quarter of the speed of light. That's about 45,000 miles per second. For comparison, a bullet travels somewhere around half a mile per second. The infalling material is moving about 90,000 times faster than that. This isn't a gradual process. It's a catastrophic freefall with nothing to slow it down. As the core compresses, the pressure becomes so extreme that something unusual happens at the atomic level. Electrons are literally forced into protons. This process is called electron capture. The electron and the proton merge, producing a neutron and releasing a neutrino. It happens everywhere throughout the collapsing core at once. Protons disappearing, neutrons forming, neutrinos streaming outward. The core is being transformed at the most fundamental level, converting ordinary matter into something almost unrecognizable. What started as an iron core is rapidly becoming a dense ball of neutrons, and with every neutron produced, another neutrino is released. These neutrinos aren't a minor byproduct. They're one of the most extraordinary parts of this entire event, and most people don't fully appreciate just how many of them are created. In the span of a few seconds surrounding this collapse, the dying star produces more neutrinos than the sun will emit across its entire 10 billion year lifetime. More than 10 billion years of solar neutrino output, compressed into moments. That number is genuinely difficult to hold in your head. Neutrinos are nearly massless particles that interact almost not at all with ordinary matter. They pass through walls, through planets, through you, without leaving any trace, normally. But the density inside this collapsing core is so extreme that even neutrinos, particles that could ordinarily pass through a light year of solid lead without stopping, are briefly trapped. The matter is packed so tightly that nothing moves freely. The neutrinos eventually escape, and when they do, they carry off an enormous fraction of the total energy released. But the core itself is still collapsing. The density the core reaches during this process is something our physical intuition simply can't process. At nuclear density, the density of an atomic nucleus, the neutrons resist being compressed any further. This resistance is called neutron degeneracy pressure. It's the same basic quantum mechanical principle that previously applied to electrons, now applying to neutrons. And for a brief moment, this pressure is enough to halt the collapse. The core stops. Just like that. After freefall, at a quarter of the speed of light, the inner core suddenly stops compressing. What was a catastrophic inward rush hits a wall. The densest material in the known universe, compressed to nuclear density, becomes nearly incompressible. A single teaspoon of this material would weigh approximately 1 billion tons. 1 billion tons. Think about that for a moment. A teaspoon, the kind you'd use to stir coffee in the morning, filled with material from this collapsed core. It would outweigh every building ever constructed by human civilization combined, many times over. We have no real reference for it. Our brains didn't evolve to process densities like that. But the physics is real. The collapsed core has achieved a density that exceeds anything else we can point to in the observable universe, short of a black hole itself. And here's where something remarkable happens. The inner core doesn't just stop, it bounces. The neutron degenerate matter is so stiff and so resistant to further compression that the infalling outer layers hit it and rebound outward. The core overshoots its equilibrium point and springs back. This rebound is called the core bounce. It's one of the most consequential single events in stellar physics. The inner core, having halted its collapse, now pushes back against everything still falling inward. The outer layers of the iron core have been streaming inward this entire time. They haven't stopped. They're still crashing inward at enormous speed when they collide with this newly rigid, neutron-dense inner core. That collision generates a shock wave, not a gentle pressure wave. A violent outward-moving wall of energy tearing through layers of iron that are still falling in the opposite direction. Two enormous forces now moving directly toward each other. The shockwave doesn't know yet what's waiting for it out there in the star's outer layers. It just drives outward with the full energy of that core rebound behind it. While all of this is happening, the temperature inside the collapsing core spikes to levels that have no parallel anywhere in the current universe. The core briefly reaches temperatures in the range of hundreds of billions of degrees. Hundreds of billions. To give that any scale, the surface of our sun sits at about 10,000 degrees Fahrenheit. The core of the sun reaches about 27 million degrees. This collapsing stellar core, in its final moments, reaches temperatures more than 10,000 times hotter than the sun's center. Nothing else in the universe right now is that hot. It's hotter than any object that has existed since the very first moments after the Big Bang. The material is no longer behaving like anything described in ordinary physics. Its plasma stripped of all familiar structure, compressed beyond any everyday description. There's another consequence of this collapse that we've only recently confirmed directly. If the collapse isn't perfectly symmetric, and it rarely is, the collapsing core emits gravitational waves. These are ripples in the fabric of space-time itself. Einstein predicted them in 1915. We didn't detect them directly until 2015. Core collapse events like this one are among the sources that gravitational wave detectors were specifically built to find. The waves carry information about the collapse that no other signal can provide. Light can't escape from inside the star during those first moments. Neutrinos can barely escape. But gravitational waves pass through everything. They carry a direct physical record of how the core moved, how asymmetric the collapse was, and how the bounce actually proceeded. They are the most honest witness to what just happened down there. The proto-neutron star that forms in those first moments is extraordinary by any measure. It's roughly 12 to 15 miles in diameter. It contains more mass than our entire sun. It's rotating, possibly very rapidly, depending on how much angular momentum the original core carried. And it's sitting at the center of a star that is still almost entirely intact. The outer layers, the hydrogen envelope, the helium shell, the other burning layers further out, haven't gone anywhere. They didn't even register that the core had collapsed. The information about what just happened hasn't had time to reach them. Light takes time to travel. Pressure waves take time to travel. The outer star is still in freefall, still collapsing inward, completely unaware of what has already formed at its center. This is one of the stranger aspects of the collapse to sit with. The star might span hundreds of millions of miles from edge to edge. The core just collapsed in under a second, but the outer layers are light minutes away from the center, and causality is absolute. Information cannot travel faster than light. So the outer star doesn't react, it keeps falling. The shockwave is now moving outward through that infalling material, trying to reach those distant layers. Whether it makes it, whether it has enough energy to punch all the way through is the question everything that follows depends on. But right now, inside this first second, we have a proto-neutron star, a flood of neutrinos, temperatures beyond anything else in the cosmos, and a shock wave driving outward through still collapsing material. What just happened in under a second represents one of the most extreme transformations of matter in the history of the universe. A stellar core the size of Earth is now a ball of neutrons 12 miles across. The density increased by a factor that would require many lines of zeros to write out properly. Speeds approaching a quarter of the speed of light. Temperatures in the hundreds of billions of degrees. Gravitational waves already rippling outward through space-time in all directions. And somewhere out in the still infalling layers of what was once a massive burning star, a shock wave is tearing outward with the energy of that core rebound driving it forward. In less than a second, matter has been compressed so violently that space-time itself begins to react, and the shock wave is racing, jagged outward through the still falling star. The shock wave tears outward through the star at a significant fraction of the speed of light, and for a brief moment, it seems like it might make it. The core has bounced. The rebound is moving. There's real energy behind it, enormous energy, and it's headed straight through the outer layers of the star at speeds that would cross the continental United States in a fraction of a millisecond. From the outside, nothing is visible yet. The star looks exactly as it did a second ago. But deep inside, something extraordinary is happening. A wall of pressure racing outward from a collapsed core, carrying with it the potential to either destroy the star in one of the universe's most spectacular explosions, or fail quietly and leave behind something far darker. Here's the problem. The shock wave doesn't travel through empty space. It travels through a star, and a star is full of material. As the shock wave pushes outward, it slams into the layers of iron that are still falling inward toward the core. Those in falling iron nuclei don't just get pushed aside, they get destroyed. The shock wave carries enough energy to photodisintegrate them, to rip apart iron nuclei that took millions of years of stellar fusion to build. That process costs energy, a lot of it. Every iron nucleus the shock wave tears apart pulls momentum away from the wave itself. The shock wave is essentially spending itself to destroy its own path forward. That's already a serious problem. But it gets worse. At the same time this is happening, the newly formed proto-neutron star at the center is radiating neutrinos in quantities that are almost impossible to express. Neutrinos are nearly massless particles that barely interact with anything. Normally, they pass through matter as if it weren't there at all. Trillions of solar neutrinos pass through your body every second without you noticing. But the densities inside a collapsing stellar core are so extreme that even neutrinos get trapped briefly before escaping. When they do escape, they carry energy with them, and a significant fraction of that energy should, in theory, be deposited back into the shock wave as the neutrinos stream outward through it. That's actually one of the mechanisms that could save the shock wave. But it has to work. It doesn't always work. For a large fraction of massive stars, the shock wave stalls. It loses too much energy to photodisintegration. The neutrino heating isn't efficient enough to revive it. The wave runs out of momentum somewhere inside the star, maybe a few hundred miles above the core, maybe less, and it just sits there, suspended, while the outer layers of the star continue to collapse inward through it. The technical term is a stalled accretion shock. The shock wave has essentially become a standing wave, neither advancing nor retreating, while matter piles up on top of the proto-neutron star below it. This is the branching point. This is where the story goes, one of two ways. If the shock wave revives, if the neutrino heating picks back up, if turbulence behind the shock helps push it forward, if something gives it enough energy to start moving again, then it punches through. It breaks out of the star's outer layers. The outer envelope gets blasted into space. You get a supernova. The star explodes. What's left at the center is a neutron star, spinning furiously, incredibly dense but stable. That's one outcome. That's the more familiar outcome. But if the shock wave doesn't revive, something else happens. The outer layers keep falling inward. The proto-neutron star sits at the center, and mass keeps accumulating on top of it. The neutron star grows heavier and heavier. Neutron degeneracy pressure, the quantum mechanical resistance of neutrons to being compressed into the same state, is holding the whole thing up. It held the original collapsed core together. It's what made a neutron star rather than immediate black hole formation at the moment of the bounce. But neutron degeneracy pressure has a limit, just as electron degeneracy pressure had a limit before it. That limit is somewhere around 2 to 3 times the mass of our Sun. If enough material falls back onto the neutron star to push its mass past that threshold, The neutron star collapses further. There is no next stage of resistance. No known force in physics steps in at that point. The collapse continues. A black hole forms. What makes this scenario so strange, and in some ways so much harder to observe than a conventional supernova, is that it can happen almost silently. There's no spectacular explosion lighting up the galaxy. There may be a faint glow as the neutrino burst escapes. There may be a brief flash of light from the shock wave before it stalls. But the star itself, the enormous volume of it, the outer envelope that never got blown away, that all falls inward. The star doesn't explode, it implodes. And from our perspective across thousands of light years, the result can look like almost nothing at all. One moment there's a star, the next moment there isn't. Astronomers have actually seen this. In the galaxy NGC 6946, roughly 22 million light-years from Earth, a red supergiant was catalogued and monitored. It was a massive star, about 25 times the mass of our Sun. Between 2007 and 2009, it briefly brightened, consistent with a failed shock, an outburst before the collapse. Then it faded. By 2015, it was essentially gone. Not dimmed, not obscured. Gone. Where a star had been, there was now only a faint infrared glow, probably from heated dust left over from the star's final years. The star didn't explode. It didn't leave behind a brilliant nebula. It just disappeared. Astronomers designated it N6946bH1. The name tells you what they think happened. The most likely explanation is a direct collapse black hole, a star that went from existing to not existing with almost no visible announcement. That's a difficult thing to process. We're used to the idea that massive stars end with supernovae, brilliant, violent, visible across entire galaxies, and many of them do. But the most massive stars may actually be the quietest in their endings. More mass means a stronger gravitational pull on the infalling material. More mass means more momentum pushing down on the stalled shock wave, the very property that makes these stars so bright during their lives. Their enormous mass may be what prevents any final announcement when they die. They collapse so completely, so rapidly, that there's nothing to scatter outward. No explosion, no nebula, just a region of space where a star used to be, now occupied by something that bends space-time. The neutrino story is worth pausing on here. Even when a black hole forms without a visible explosion, the neutrino burst still escapes. Those neutrinos carry away an extraordinary amount of energy, roughly 10 times more energy than the Sun will radiate across its entire 10 billion-year lifetime, released in roughly 10 seconds. We detected exactly this kind of neutrino burst from supernova 1987A in the Large Magellanic Cloud, a conventional core collapse event. And it confirmed the theoretical picture in remarkable detail. If a massive star in or near our galaxy collapsed directly to a black hole tomorrow, neutrino detectors on Earth would see it before any optical telescope could. The neutrinos arrive before the light. In a failed supernova, they might be the only signal we get. The shockwave revival process is one of the most active areas of research in computational astrophysics right now. Simulating it requires modeling the behavior of dense nuclear matter, radiation transport, neutrino physics, magnetohydrodynamics, and general relativity simultaneously in 3 dimensions at timescales shorter than milliseconds. Even with modern supercomputers, this is extraordinarily difficult. We don't yet have a complete, reliable model that predicts exactly which stars produce supernovae and which collapse directly. The mass of the progenitor star matters. The rotation rate matters. The magnetic field matters. Whether the star had a companion star matters. Small differences in initial conditions can push a star from one outcome to the other. The universe, it turns out, has a complicated set of criteria for deciding which stars get to go out loudly. For some stars, there is no explosion, just a star that was there and then isn't. swallowed by what it became. When the neutron star's mass crosses the threshold that neutron degeneracy pressure can no longer hold, there is no next stage of resistance. That's worth sitting with for a moment. Every other crisis the star has faced, it has found a way to push back. Gravity crushed the hydrogen core, and fusion ignited. Gravity crushed the helium core, and carbon burning began. The iron core collapsed, and electron degeneracy pressure slowed things down. Then neutrons packed together and pushed back against the compression. Each time, the universe offered something, a new force, a new reaction, another temporary answer to the same relentless question gravity keeps asking. But now, past roughly 2 to 3 solar masses of accumulated material pressing down on the proto-neutron star, there is no new answer. Neutron degeneracy pressure fails, and nothing in the known laws of physics can take its place. The collapse resumes. There is no bounce this time, no rebound, no shock wave launching outward from this new compression. The material just falls, inward, faster, denser. The neutron star, already one of the most extreme objects in the universe, begins shrinking further. The density climbs past anything we have a name for. Our equations are still technically working at this point, still producing numbers, still describing the geometry of what's happening. But the numbers are heading somewhere our intuitions cannot follow. The density is increasing without any apparent ceiling. The gravitational field at the surface of the collapsing object is growing stronger by the moment. And at some point during this process, something happens that has no parallel anywhere in ordinary experience. The escape velocity reaches the speed of light. Escape velocity is the speed you need to reach in order to leave a gravitational field without further propulsion. From Earth's surface, that's about 25,000 miles per hour. From the surface of the Sun, it's much higher. But from the surface of a collapsing stellar core in its final moments, it climbs past 186,000 miles per second. That's the speed of light. That's the universal speed limit. Nothing travels faster. When the escape velocity at the surface of the collapsing object exceeds the speed of light, that surface becomes something new. It becomes an event horizon. And at that moment, the black hole is born. Here's what the event horizon actually is. It's not a wall. It's not a physical barrier you could touch or feel or detect by running your hand along it. It's a mathematical boundary in space-time, a surface defined entirely by geometry. Inside that boundary, every possible path through space-time, every trajectory any particle or photon could take, curves inward. Not just downward, not just toward the center, but inward in every direction. There is no path out, not a difficult path, not a path requiring more energy than we have available. There is simply no path. The geometry of space-time inside the event horizon does not permit outward motion in any direction. Light, which moves in straight lines through flat space-time, curves inward here. Light cannot escape, and if light cannot escape, nothing can. This is what makes a black hole genuinely different from anything else in the universe. It's not just an extremely dense object. It's a region of space-time that has become causally disconnected from the rest of the universe. Whatever falls past the event horizon is gone. Not gone the way something disappears behind a wall, where it still exists on the other side. Gone in the sense that no signal, no light, no gravitational information, no message of any kind can ever travel from inside the horizon to outside it. The matter is still there. The mass is still real. The physics continues, but the inside of the event horizon and the outside are separated by something more fundamental than distance. They are separated by causality itself. Think about what that means for an object falling in. As it crosses the event horizon, nothing dramatic happens at the boundary. There's no surface to hit, no wall to strike. If you were somehow falling toward a black hole, you would cross the event horizon without noticing it. You would cross the point of no return, and the universe outside would continue looking roughly normal for at least a short time. But from outside, no one would ever see you cross. The light carrying the image of your crossing would be trapped along with you. An observer watching from a safe distance would see you slow down, redden, dim, and appear to freeze at the horizon forever, never quite arriving. Time dilation at the extreme gravitational boundary stretches the image outward over an infinite span of time. From your own perspective, you crossed in a moment. From theirs, you never finished crossing. At the center of the newly formed black hole sits the singularity. A singularity is where the equations of general relativity stop producing useful answers. They produce infinities instead. Infinite density, infinite curvature of space-time. A point of zero volume containing all the mass of the collapsed stellar core. General relativity is one of the most precisely tested theories in science. It has passed every experimental check we've ever thrown at it. But at the singularity, it returns not a description of reality, but a mathematical breakdown. Most physicists interpret this not as proof that the singularity is literally a point of infinite density, but as evidence that general relativity is incomplete. That at densities this extreme, a theory combining general relativity with quantum mechanics, one we don't fully have yet, would be needed to describe what's actually there. The singularity is, in a very real sense, the edge of our understanding. The black hole that forms from a stellar collapse is small, startlingly, almost absurdly small, given what produced it. The star that collapsed might have been 20, 30, 40 times the mass of our Sun, a star with a radius of millions of miles, a star so large that if you placed it in our solar system, it would extend well past the orbit of Earth. That entire object, with all its mass, all its volume, all its millions of years of fusion history, collapses down to an event horizon roughly 10 to 20 miles across. That's it. A sphere smaller than most cities. The Schwarzschild radius for an object of stellar mass is measured in miles, not millions of miles, not even thousands of miles. Just miles. 10 miles. That's about the distance you might drive to a grocery store and back. The event horizon of a freshly formed stellar mass black hole is smaller than that round trip. Every mountain, every ocean, every layer of a star that burned for millions of years, compressed into something you could cross in a car in under 15 minutes. If you could somehow drive across the surface of a mathematical boundary in curved space-time, the mass hasn't gone anywhere. That's the thing that's hardest to hold in your mind. The gravity is still there. The black hole exerts a gravitational pull on everything around it. If the sun somehow collapsed into a black hole right now, the planets would continue orbiting exactly as they do today. The mass would be the same. The orbits would be unchanged. The difference is that the mass would now be contained within an event horizon. The light would stop. The fusion would stop. The sun would simply be gone, replaced by a dark region of space a few miles across with the same gravitational influence it had before. What's inside the event horizon continues to collapse. The matter doesn't stop at some new equilibrium. There's no force to create one. The collapse proceeds toward the singularity. All of it. All that mass. All that history. Focused to a point. The event horizon expands slightly as more infalling mass crosses it, pushing the boundary outward by a tiny amount with each addition. But the event horizon itself is already formed. The black hole already exists. What was a star a fraction of a second ago is now this, a sphere of space-time a few miles across, from which nothing, not light, not information, not any signal of any kind, will ever escape again. When the shock wave survives, when it has enough energy to punch through the infalling layers and escape, the result is one of the most spectacular events in the observable universe. The outer layers of the dying star, which moments before were still falling inward, get reversed. The shock wave hits them and accelerates them outward at thousands of miles per second, not hundreds of miles per second, thousands. Material that spent millions of years sitting quietly inside a star gets flung into space in a matter of hours. The star tears itself apart from the inside out. What's left expanding into the surrounding void is a supernova. The energy involved is almost impossible to express. In the first few seconds of the explosion, the collapsing core releases more energy than the Sun will produce across its entire 10 billion-year lifetime. The Sun has been burning for 4.6 billion years. It will burn for another 5 billion. All of that energy, the full sum of it, is exceeded by what a core collapse supernova releases in roughly 10 seconds. Most of that energy comes out as neutrinos, which stream straight through the star and into space. But even the small fraction that goes into the explosion itself is enough to blow a star to pieces. For a few weeks, a single dying star can outshine every other star in the galaxy combined. An entire galaxy, hundreds of billions of stars, all of them burning at once, and one supernova can match the light output of the whole thing. From a distant galaxy, astronomers watching through a telescope might see a faint smear of light suddenly develop a new point in it. That point is a star dying. It's one object among hundreds of billions, briefly shining as bright as all the others put together. We don't have to look to distant galaxies for evidence of this. History recorded one of the most famous supernovae directly. In July of 1054, Chinese astronomers documented the appearance of a new star in the sky. It wasn't faint or ambiguous. It was bright enough to see during the day. For roughly 3 weeks, you could look up at midday and find it glowing in daylight. At night, it cast faint shadows. It remained visible to the naked eye for nearly 2 years before finally fading. What those astronomers were watching was a star dying about 6,500 light-years from Earth. The light from that death had been traveling toward us for over 6,000 years. When it finally arrived, people noticed it without any telescope at all. Today, we can point a telescope at where that star used to be. What we find there is the Crab Nebula. It's an expanding cloud of gas and debris, roughly 11 light-years across, still spreading outward nearly 1,000 years after the explosion. At the center of it sits a pulsar, a rapidly spinning neutron star, the collapsed remnant of the core that triggered the whole event. It rotates about 30 times per second. That neutron star is what was left when the shock wave succeeded and the outer layers were thrown into space. The 1054 event isn't the only recorded supernova in our galaxy's history. In 1604, a new star appeared in the constellation Ophiuchus. Johannes Kepler observed it carefully and documented it. It got bright enough to rival Jupiter and was visible to the naked eye for over a year. Kepler's supernova, as it became known, was the last supernova in the Milky Way visible without a telescope. That was more than 400 years ago. Here's what that means. On average, astronomers estimate a supernova should occur somewhere in our galaxy every 50 to 100 years. We are, by that estimate, long overdue. There are likely supernovae happening in the Milky Way right now, hidden behind dense clouds of gas and dust that block the light from reaching us. We can sometimes detect them in other wavelengths, but we haven't had a naked eye event in our own galaxy in 4 centuries. At some point, that will change. There is almost certainly a massive star somewhere within a few thousand light-years of us that is weeks or years or centuries away from crossing the iron threshold and going through everything described in the previous sections. The observational signatures of these distant explosions have revolutionized our understanding of stellar physics. Astronomers studying supernovae in other galaxies use them as cosmic distance markers. The brightness and light curve characteristics of specific supernova types allow researchers to measure how far away galaxies truly are. This method has been refined over decades of observations and has become one of the most powerful tools in cosmology. The energy released, the composition of ejected material, and the properties of the remnant left behind all provide clues to the star's initial mass and the mechanisms driving the explosion. Modern telescopes observing across multiple wavelengths from infrared through ultraviolet and even X-rays have revealed that supernovae are more complex and varied than once believed. When a supernova like this one fades, it doesn't leave nothing behind. It leaves two things. The first is the remnant itself, an expanding shell of gas and heavy elements moving outward at thousands of miles per second, growing and cooling over thousands of years, eventually spreading across dozens of light years of space. Nebulae like the Crab aren't decorative. They're the debris fields of stellar catastrophes. They're clouds of carbon, oxygen, silicon, calcium, iron, elements that didn't exist in the universe until stars spent millions of years building them up, layer by layer, through the fusion stages we walked through earlier. That material is now loose in space, mixed with the surrounding interstellar medium, available to become part of whatever forms next. The second thing left behind is the compact remnant at the center. For lower-mass progenitor stars, that remnant is a neutron star. Dense, spinning, sometimes pulsing with beams of radiation that sweep across space like a lighthouse. For higher-mass cores, the remnant may be a black hole. The difference comes back to that mass threshold. If enough material falls back onto the neutron star after the initial explosion, or if the core was simply too massive from the start, neutron degeneracy pressure fails and the collapse continues. But in either case, the outer layers of the star are already gone. They're spreading outward, and in that expanding cloud is everything. Carbon atoms, oxygen, nitrogen, silicon, iron, the same elements that appear in the periodic table, the same ones that make up soil and oceans and living tissue, scattered across interstellar space by the violence of a dying star. New clouds of gas and dust will eventually collect some of this material. Gravity will pull those clouds inward. New stars will form, and around some of them, planets. On some of those planets, conditions might allow chemistry to get complicated, and the atoms that were once inside a star, forged over millions of years of nuclear fusion and then flung outward by a shock wave, will end up in unexpected places. Every atom of iron in your blood was forged in a stellar core and scattered across space by an explosion exactly like this one. For most of the history of astronomy, black hole formation was a story we told entirely from equations. We had the physics, we had the mathematics, we had general relativity pointing us toward this inevitable conclusion that stars massive enough would eventually collapse past the point where any force could stop them. But actually watching it happen was a different matter entirely. These events occur inside collapsing stellar cores, hidden behind billions of tons of infalling gas and dust, buried in some of the most extreme environments the universe produces. For a long time, we could only infer that they happened. We could study the aftermath. We could find the black hole sitting there afterward and work backwards. But the birth itself? That remained invisible to us. Here's what most people don't realize. We've only recently crossed the threshold from inference to observation. And the events that got us there are remarkable. They didn't arrive in the way anyone quite expected. They didn't announce themselves cleanly. They required careful analysis, repeated measurements, and a willingness to sit with data that initially looked confusing. But they're real, and they changed what we can honestly say we know about how black holes come into existence. The first case worth examining is a supernova called SN2-022JLI. It was detected in 2022 in a galaxy called NGC 157, and at first it looked like a fairly ordinary core collapse supernova. A massive star had died. The explosion had been observed. That part was not unusual. What made SN2-022JLI different emerged slowly, buried in the light curves coming back from the event. The brightness of the supernova wasn't simply fading the way most supernovae fade. It was oscillating. There was a rhythm to it, a periodic signal repeating roughly every 12 days, embedded in the fading glow of the dying star. Astronomers measured it again and again. The signal kept coming back the same. The explanation, once it was worked out, was striking. The star that had exploded wasn't alone. It had a companion, a second star orbiting nearby, a binary partner that had survived the explosion, and the compact object left behind by the collapse, whether a neutron star or a black hole, was interacting gravitationally with that companion on every orbit. As the companion swung around, it was donating material to the compact object. That material was spiraling inward and releasing energy. The interaction was periodic. The orbit was the clock, and that rhythmic signal in the light was the heartbeat of something newly born at the center of the explosion. For the first time, astronomers had watched not just a supernova, but the object the supernova left behind, identified in real time through its gravitational relationship with the star it had outlived. SN2-022 ESA told a different story. Where SN2-022 JLI was subtle, this one was loud. The progenitor star was a Wolf-Rayet star. These are extraordinary objects. Wolf-Rayet stars are so massive, so intensely luminous, that their own radiation drives powerful stellar winds off their outer surfaces. They shed their hydrogen envelopes entirely. What's left is the bare, exposed core of a star. Hot, dense, furiously active. Wolf-Rayet stars are already stripped down to their essentials by the time they approach collapse. When they go hard. SN2.022 ESA was classified as a type ICCSM supernova. That means the exploding star had no hydrogen envelope left, and it exploded into a dense shell of circumstellar material, gas and dust that the star had shed through its stellar winds before it died. The shock wave from the explosion slammed into that material and lit it up. The result was an energetically bright event, observable across an enormous distance, producing electromagnetic signals that made it possible to classify the explosion and identify the likely progenitor. Earlier theoretical models had suggested that when a very massive star collapses directly into a black hole, the event might be relatively dim. SN2-022 ESA pushed back against that. Black hole birth is not necessarily quiet. Some of these events are bright enough to see across hundreds of millions of light years. Then there's N6946BH1. This one is different in character from both of those events. There was no explosion. There was no periodic signal in the aftermath. There was, in the most literal sense, almost nothing. And that absence is precisely what made it remarkable. 96946BH1 was a red supergiant in the galaxy NGC 6946, which sits about 22 million light-years from Earth. Between 2009 and 2015, astronomers were monitoring it as part of a survey tracking massive stars. In 2009, it was there. Luminous, visible. A large star at the late stage of its life. By 2015, it was gone. Not faded, gone. Where a bright star had been, there was only a faint infrared glow. No supernova had been recorded. No explosion had been detected. The star hadn't wound down slowly the way dying stars sometimes do. It simply ceased to be a visible object. The infrared glow left behind is consistent with material that had been shed by the star before its disappearance. Still faintly warm, still faintly glowing, but the star at the center was no longer there. The most likely explanation is a failed supernova. The core collapsed. The shock wave that should have blown the outer layers away never made it out. The mass fell back. Neutron degeneracy pressure failed, and the entire star was swallowed by the black hole that formed at its core, directly, without announcement. 19694-6BH1 is one of the strongest candidate cases we have for a star that became a black hole without producing a conventional supernova. A disappearing act that would have been invisible to us entirely if we hadn't been watching that particular star in that particular galaxy at that particular time. 19C 6946 itself has been nicknamed the Fireworks Galaxy because it has hosted an unusually high number of observed supernova over the last century. 10 confirmed supernova in roughly 100 years of observation. That concentration of stellar deaths in a single galaxy has made it a productive target for exactly this kind of survey work. And it produced, alongside all those spectacular explosions, at least one star that went out without a bang. Gravitational wave detectors have added another layer entirely. LIGO and Virgo, the instruments that first detected gravitational waves in 2015, were built to observe a different class of events, the mergers of already formed black holes and neutron stars. But the physics connects. When a stellar core collapses asymmetrically, the uneven distribution of mass radiates gravitational waves. Space-time ripples outward from the collapse itself. The signals would be weak at the distances involved, and current detectors aren't yet sensitive enough to confirm a direct detection of a stellar collapse in another galaxy. But the technology is improving. Future generations of detectors may be able to identify the gravitational wave signature of a core collapse in real time, adding an entirely new observational channel to the ones we already have. What's changed in the last decade is not the underlying physics. The equations haven't been rewritten. The processes happening inside a collapsing stellar core are the same ones theorists worked out decades ago. What's changed is our ability to actually see evidence of those processes in action. We now have a star that vanished. We have a supernova with a heartbeat. We have a Wolf-Rayet collapse that blazed brightly enough to challenge our assumptions about how quiet black hole birth can be. Each of these events arrived with its own complications, its own uncertainties, its own requirement for careful interpretation. None of them handed us a clean answer, but together they represent something genuinely new, a transition from a science built almost entirely on inference to a science that is beginning to gather direct evidence. Now, for the first time in human history, we are beginning to watch it actually happen. Stellar collapse is the most familiar route to a black hole, but the universe has been making them through other means since the very beginning. The process we've described so far, a massive star burning through its fuel, an iron core collapsing, a shock wave either succeeding or failing, that's the dominant mechanism in the universe today. It's the path most stellar mass black holes take, but it requires stars to already exist. Stars require time to form, and in the very first moments after the Big Bang, there were no stars at all. The universe was just a hot, dense, expanding soup of matter and energy, and yet, even then, the conditions for black hole formation were present. Here's what most people don't realize. The early universe wasn't perfectly smooth. It was lumpy. Tiny variations in density existed everywhere, regions where matter was slightly more concentrated than the surrounding space. In most cases, these fluctuations were small enough that the expansion of the universe simply carried them apart before gravity could take hold. But in some regions, the density was high enough that gravity won. The materials stopped expanding outward and began collapsing inward instead. No star formed first, no fusion ignited. The matter just compressed directly into a black hole. These are called primordial black holes. They could have formed within fractions of a second of the Big Bang, and because they weren't constrained by the physics of stellar collapse, no Chandrasekhar limit, no minimum core mass, they could form with almost any mass at all. A primordial black hole forming at the Planck time, roughly 10 to the negative 43 seconds after the Big Bang, would have had a mass close to the Planck mass itself, something vanishingly small by any ordinary measure. A primordial black hole forming about 1 second after the Big Bang could have had a mass of roughly 100,000 times the mass of our Sun. The same basic process. Wildly different outcomes. The early universe was that varied in its extremes. We haven't confirmed that primordial black holes exist. No one has directly detected one, but they remain a serious candidate for part of the dark matter in the universe. The theoretical case for their existence is well established. If they do exist, some of the smallest ones, those formed earliest, with the least mass, would have already evaporated over the age of the universe through a quantum process. The largest ones would still be out there, somewhere, ancient and invisible. Then there's a second path, the first generation of stars. Astronomers call them population 3 stars, and they were unlike anything that exists today. The early universe contained only hydrogen and helium, the elements produced in the Big Bang itself. No carbon, no oxygen, no iron. The heavier elements didn't exist yet because no stars had lived and died to create them. Population 3 stars formed from this pure primordial gas. Without heavier elements to radiate heat away and slow the collapse of the gas clouds, these stars could accumulate extraordinary amounts of mass before fusion ignited. Estimates suggest some of them were hundreds of times more massive than our Sun, possibly thousands of times more massive than our Sun, possibly thousands of times more massive than our Sun. A star 1,000 times the mass of our Sun doesn't live long. It burns through its fuel at a ferocious rate. Its life might last only a few million years compared to the billions of years available to stars like our Sun. And when it dies, the collapse is proportionally catastrophic. The core masses involved far exceed anything seen in present-day stellar collapses. These weren't the kind of events that produce neutron stars. The cores were simply too massive. They collapsed directly into black holes. They did it early, within the first few 100 million years of cosmic history. Those black holes became seeds, the universe's first black holes, scattered through the earliest galaxies, ready to grow. That growth is the third mechanism worth understanding: direct collapse. Even without a star forming first, vast clouds of primordial hydrogen and helium could have collapsed under their own gravity in the right conditions. If a gas cloud was massive enough, if it was prevented from fragmenting into smaller clumps, which normally happens when gas cools and contracts, the entire cloud could fall inward as a single object. No stellar core, no fusion chain, no iron catastrophe. Just an enormous cloud of gas becoming an enormous black hole in a single gravitational event. The black holes produced this way would start their lives already enormously massive, perhaps 100,000 times the mass of our Sun, far too large to have formed through stellar collapse. This direct collapse scenario matters because it potentially solves a serious problem. When astronomers look at the most distant quasars in the universe, objects so far away that we're seeing them as they were less than 1 billion years after the Big Bang, some of them contain black holes with masses of 1 billion solar masses or more. 1 billion solar masses, built in under 1 billion years. If those black holes started as stellar mass objects of 10 or 20 solar masses, they would have had to double in mass roughly every 30 million years or so, continuously without pause for the entire first billion years of cosmic history. That's possible in principle, but it's extremely difficult to arrange in practice. Direct collapse would give those black holes a much larger head start. And yet, even with stellar collapse, primordial black holes, population 3 stars, direct collapse, all potentially contributing, there's a problem. If supermassive black holes grew from smaller seeds, through mergers, and through pulling in surrounding gas over billions of years, we should be able to find objects in the middle, objects between a few hundred solar masses and a few million solar masses, intermediate steps on the way from stellar mass to supermassive. These are called intermediate mass black holes, and they are almost entirely absent from our observations. We have a handful of candidates, none fully confirmed. There are galaxies with central black holes in the right mass range. There are some unusual X-ray sources in nearby galaxies that might qualify. But for something that should be relatively common, if supermassive black holes grew gradually, intermediate mass black holes are conspicuously rare. Either we're missing them because they're hard to detect, small enough not to dominate their host galaxies, far enough away to blur together with other sources, or the growth of supermassive black holes didn't proceed through the gradual accumulation we assumed. Maybe the direct collapse pathway was more common than it appears. Maybe population 3 stars produced black holes massive enough to skip much of the intermediate stage entirely. Maybe the mergers and accretion happened so rapidly in the early universe that intermediate mass black holes represent only a brief phase, lasting a few 100 million years before they grew beyond it. We genuinely don't know. And somewhere between the stellar mass black holes we understand fairly well and the supermassive monsters sitting at the centers of galaxies, there's a gap in our observations that we haven't fully explained. To understand what a black hole actually is, not just that it exists, but what it means, you have to sit with the physics for a moment. Most people think of a black hole as a thing, a dense object sitting in space, pulling everything toward it. And in some sense that's true, but it misses what makes black holes genuinely strange. A black hole is not simply a very compact star, it's a feature of space-time itself, a region where the geometry of the universe has been bent so severely that the normal rules no longer apply. The event horizon isn't a surface you could stand on. It isn't a wall. There's no material there. No barrier you could touch. It's a mathematical boundary, a threshold in the structure of space and time past which the future only points inward. That distinction matters. Here's what most people don't realize. Every object in the universe has what's called a Schwarzschild radius. Every single one. The Earth's Schwarzschild radius is about 9 millimeters. That means if you could somehow compress all of Earth's mass, every ocean, every mountain, every cubic mile of rock and iron in the planet's core, into a sphere 9 millimeters across, the escape velocity at that surface would exceed the speed of light. Earth would become a black hole. The Sun's Schwarzschild radius is about 3 kilometers. 3 kilometers, a star 864,000 miles across, compressed to something 6 kilometers in diameter. That's the threshold. The reason Earth and the Sun aren't black holes isn't that they lack the mass. It's that their mass is spread out far beyond those radii. You never get close enough to the center for the escape velocity to reach the speed of light. You're always on the outside, but compress the mass inside that radius, and the event horizon forms. The black hole exists. This is what happens during stellar collapse. The core of a massive star, already compressed to nuclear densities, crosses its own Schwarzschild radius during the final stages of collapse. The event horizon forms. It forms not as a dramatic visible boundary, but as a quiet geometric fact. A sphere of space-time where outward escape becomes impossible. The star above it keeps falling in. The black hole grows. Now consider what it would actually be like to fall toward one. There are two very different answers, depending on where you're watching from. From a safe distance, watching someone fall toward the event horizon, you would never see them cross it. Gravity distorts time. The closer you are to an extreme gravitational field, the slower time passes for you relative to someone far away. This is gravitational time dilation. It's real. We measure it here on Earth. GPS satellites have to account for it, or their positions drift. Near a black hole, the effect becomes extreme. As an infalling observer gets closer to the event horizon, their clock runs slower and slower from your perspective. Their image gets dimmer, redder, more stretched. They appear to slow down, freeze. They never quite reach the horizon from your point of view. They hover there forever, fading. But from their own perspective, the experience is completely different. They cross the event horizon without noticing. There's no wall, no flash of light, no physical sensation marking the boundary. For a large enough black hole, tidal forces at the horizon are actually quite gentle. They fall through, and then they continue falling toward the center. At that point, the singularity isn't a place in space. It's a moment in their future. It is as inevitable as tomorrow. No matter what they do, no matter what direction they accelerate, their future leads there. The singularity. That word carries a specific meaning in physics, and it's not a comfortable one. At the center of a black hole, according to general relativity, the density becomes infinite. The curvature of space-time becomes infinite. The equations that describe gravity return not a finite answer but a breakdown, a division by zero. Physicists call these results singularities, and they generally interpret them as a sign that the theory has been pushed past its own limits. General relativity, which describes gravity with stunning accuracy everywhere we've tested it, stops working here. It gives us infinities. And infinities in physics usually mean we're missing something. What we're missing is a theory of quantum gravity. General relativity governs the very large, planets, stars, black holes, the curvature of space-time across cosmic distances. Quantum mechanics governs the very small, particles, fields, the probabilistic behavior of matter at atomic and subatomic scales. These two frameworks have both been tested to extraordinary precision. They both work, but they are fundamentally incompatible with each other at the mathematical level. Combining them into a single consistent theory is one of the deepest unsolved problems in all of physics. String theory, loop quantum gravity, and other approaches are attempts to build that unified framework. None has been confirmed. At the singularity inside a black hole, both frameworks become necessary at once. Extreme, gravity, and extreme quantum effects in the same region of space. Without quantum gravity, we genuinely cannot say what happens there. This isn't a minor gap. It's the center of a black hole. It's the end point of stellar collapse. It's the thing the rest of the collapse is building toward, and we don't know what it is. Hawking radiation enters the picture here. In 1974, Stephen Hawking combined quantum mechanics with general relativity in a limited way. Not a full theory of quantum gravity, but a calculation that treated the space-time around a black hole as a fixed background and asked how quantum fields behave in that background. The result was remarkable. He found that black holes aren't completely black. They should emit radiation, a slow, faint trickle of thermal radiation produced by quantum effects right at the event horizon. The mechanism involves virtual particle pairs that spontaneously appear and annihilate near the horizon. Sometimes one falls in while the other escapes. The escaping particle carries energy. The black hole loses mass. Slowly. How slowly? For a stellar mass black hole, the temperature of Hawking radiation is so low, it's essentially unmeasurable. Far colder than the cosmic microwave background radiation that fills all of space. A black hole formed from a collapsing star would absorb far more energy from the surrounding universe than it would lose through Hawking radiation. It would be growing, not shrinking. The evaporation timescale for a stellar mass black hole is something on the order of 10 to the power of 67 years. The current age of the universe is about 14 billion years. Write that out. The universe hasn't even come close. The black hole will still be there, essentially unchanged, long after every star in every galaxy has burned out, long after the last red dwarf has exhausted its fuel and gone dark, long after protons themselves may have decayed, if current theories about that are correct. And yet, Hawking radiation means that evaporation eventually happens. Given enough time, unimaginable, incomprehensible amounts of time, even a black hole radiates away its mass and disappears. The information paradox that follows from this, whether information falling into a black hole is truly destroyed or somehow encoded in the radiation that escapes, remains one of the most debated questions in theoretical physics. It sits at the boundary between quantum mechanics and general relativity, exactly where our understanding runs out. The Schwarzschild radius, the event horizon, the singularity, Hawking radiation, these aren't science fiction. They're the physical consequences of mathematics we've tested and confirmed. They describe what actually forms when a massive star collapses. What's strange is not that physics produces these results. What's strange is that the universe actually goes through with it. Even the black hole, the end point of all that violence, is ultimately temporary, though it will outlast every star that currently shines by trillions upon trillions of years. When the collapse is over, when the black hole exists and the supernova has either blazed outward or failed, what's left behind tells a story about everything that came before it. Think about what a supernova actually scatters into space. The outer layers of a massive star, everything above the iron core, get blasted outward at thousands of miles per second. That material carries with it every element the star spent its entire life building. Carbon forged in the helium-burning phase, oxygen, neon, magnesium, silicon, iron, all of it. Elements that didn't exist before the star lived, now hurled across light years of space, mixing with the surrounding gas clouds of the galaxy. The interstellar medium gets richer, heavier, more chemically complex than it was before. And that matters enormously for what comes next. The ejected material doesn't travel evenly in all directions. The supernova explosion channels energy preferentially along the rotation axis of the original star, creating a pattern that's far more complex than a simple spherical blast. The shock wave encounters the surrounding interstellar medium, which has its own density variations and magnetic fields. These structures shape the expanding remnant into asymmetrical, sometimes chaotic geometries. Within decades, the fastest material is racing outward at speeds exceeding 30,000 kilometers per second. Within centuries, the remnant begins to cool and fade. The glowing gas transitions from brilliant white-hot to red to infrared wavelengths. But the chemistry persists. The iron-rich ejecta, the oxygen-enriched shells, the carbon-bearing material, all of it continues expanding, gradually mixing with the ambient medium, enriching vast regions of the galaxy with heavy elements that will influence stellar birth for millions of years to come. New stars form from that enriched gas. When a giant cloud of molecular hydrogen begins to collapse under its own gravity, it carries all of that inherited chemistry with it. The stars that form from this material are chemically different from the population 3 stars of the early universe, those first-generation objects made purely of hydrogen and helium. These newer stars, our Sun included, form with heavier elements already present. Planets form from the debris left over after the star ignites. Rocky planets. The heavier elements concentrate into solid bodies. Given the right conditions, chemistry begins. Life becomes possible. Every atom of carbon in every living thing on Earth was produced inside a star that died before our Sun was born. That's not a poetic metaphor. That's nuclear physics. The planetary compositions themselves reflect this stellar inheritance. A terrestrial planet forming in a protoplanetary disk contains iron from multiple stellar sources. Silicates processed through different nuclear pathways, trace elements that carry isotopic signatures of their original stellar origins. The magnetic fields generated by iron cores in planetary interiors, fields that protect life from stellar radiation, depend entirely on the presence of iron that a supergiant star produced and scattered. The calcium in bones, the phosphorus in DNA, the oxygen we breathe, each element has a stellar pedigree. Some came from stars that exploded 10 billion years ago, their remnants merging into the molecular cloud that became our galaxy's disk. Others came from stars that died merely a few 100 million years before our solar system formed. The chemical composition of any terrestrial world is an archaeological record of the supernovae that preceded it. The black hole itself doesn't vanish after formation. It sits at the center of whatever remains. If a supernova occurred, there's an expanding nebula around it, a shell of hot glowing gas spreading outward at thousands of miles per second, gradually cooling over thousands of years. At the center, the black hole feeds. Gas that wasn't moving fast enough to escape during the explosion falls back inward. Material from nearby regions of space drifts into the black hole's gravitational influence. It grows slowly, not quickly, not dramatically, but steadily. A stellar mass black hole might spend billions of years pulling in material one small amount at a time. Some of these black holes will eventually encounter other black holes. In dense star clusters, compact objects can sink toward the center through gravitational interactions, drawing closer over millions of years. When two black holes merge, they don't do it quietly. The merger sends gravitational waves rippling outward through space-time. We've detected these signals with LIGO and Virgo. The signals arrive here as distortions smaller than a proton. We measure them anyway, and from that measurement, we can reconstruct the masses of the two black holes that collided, how fast they were spinning, how far away the merger happened. Thousands of light-years away, two stellar remnants collide, and we feel the space-time ripple on a small planet orbiting an average star. That's remarkable. The gravitational waves themselves carry information encoded in their frequencies and amplitudes. Different frequency bands tell us different parts of the collision story. The slowly building waves before merger reveal the orbital decay phase. The sharp spike at merger captures the moment of maximum gravity. The ringing afterward, the so-called ring-down, shows the merger product settling into its final state. From these signatures, we can determine not just the masses but also the spin-angular momentum of each black hole, whether their spins were aligned or tilted relative to the orbital plane, and crucially, the distance to the event. That final measurement comes from the total energy radiated as gravitational waves, one of the most profound applications of Einstein's field equations in the modern era. Some of these merged black holes grow large enough to become the seeds of something bigger. Whether that process alone explains the supermassive black holes at the centers of galaxies remains an open question. The timeline doesn't always work, but stellar mass black holes merging and accreting over cosmic time are at least part of the story of how the universe's largest structures came to be. Here's something worth sitting with. There's a star called Betelgeuse. It's in the constellation Orion. On a clear night, you can see it with your naked eye. It's the reddish star marking Orion's left shoulder. Betelgeuse is only about 650 light-years from Earth. That's close in cosmic terms. It's a red supergiant, already in the late stages of its life, already having burned through most of its core fuel. In 2019 and 2020, it dimmed dramatically. Astronomers paid close attention. The dimming turned out to be caused by a large dust cloud ejected from the star's surface, but it was a reminder of just how actively this star is changing. Betelgeuse will explode, not necessarily soon by human timescales, but the physics is inevitable. When it does, the explosion will be visible during the day, bright enough to cast shadows at night. It will outshine everything in the sky except the sun and moon. It will remain visible for weeks, possibly months, and when the light fades, there will be either a neutron star or a black hole left at the center of an expanding nebula visible in our night sky for thousands of years afterward. That's not a distant abstract event. That's a star you can point to right now. Now think about the scale of the transformation. Betelgeuse has a radius of roughly 700 times the radius of the Sun. Its surface, if placed at the center of our solar system, would extend past the orbit of Mars. It's an enormous object. Its outer layers span hundreds of millions of miles. The volume is almost incomprehensible by any ordinary measure. And when it collapses, the core that remains, the iron core that triggers the whole catastrophe, is roughly the size of Earth. That core then collapses to something about 12 miles across. If a black hole forms rather than a neutron star, the event horizon of that black hole will be only a few miles in diameter, maybe 6 miles, maybe 8. You could drive across it in minutes at highway speed. All that mass, all that volume, all that light output over millions of years of stellar life collapsed into something smaller than a city. The radius shrinks by a factor of roughly 100 million. The density increases beyond anything our intuition can process. That's the transformation. Not destruction. Transformation. The elements scatter. The gravity concentrates. The star, in dying, seeds the galaxy with the raw materials for everything that follows. and the remnant it leaves behind warps space-time so severely that nothing escapes from within a few miles of its center. We can measure this. That's what's genuinely extraordinary here. We sit on a planet 93 million miles from an ordinary star, in an ordinary part of an ordinary galaxy, and we have built instruments sensitive enough to detect the gravitational waves from two black holes merging billions of light-years away. We have telescopes capable of watching a star disappear in a galaxy tens of millions of light-years distant and recognizing the disappearance as a direct collapse black hole formation. We can take the light arriving from a supernova, break it into its component wavelengths, and read the chemical composition of the explosion from the spectral lines. We can reconstruct what that star was made of, how massive it was, how long it lived, and what it left behind. From thousands of light-years along it lived and what it left behind. From a signal that has been traveling through space for longer than our species has existed. The atoms in the instruments we use to make those measurements were themselves produced in stellar cores. The silicon in our semiconductors, the iron in our detector housings, the carbon in our bodies, all of it came from stars that lived and died before our sun formed, scattered their contents across space, and eventually contributed their material to the cloud that collapsed to form our solar system. We are made from the remnants of stars that died exactly this way, looking up at the sky, trying to understand the violence that made us.